thought we'd go from current slide. The system is so incredibly slow. There we go. All right. My first two classes, I forgot to make the announcements. Can you imagine that? Okay. Did I make these before? I don't know if I had them last Thursday. Okay. Coming up in February, there's a couple or three sort of important things coming up in February. The first of these is February 12th, the first I know about anyway. On February 12th, which is a Wednesday, from 9:30 to 11:30, over in the Birmingham West Campus in the Building B, Academic Building, there is the Boston State College Transfer Fair Days for 2020. Okay? This is just, I think, all up and down the hall there. I don't know if you've been there for a while. They have chairs and tables set up all up and down the B hall. And here are some of the institutions that have been invited to attend. No guarantee they're all going to be here, but they either have past record or have indicated they may be interested. AUM, Mississippi State, UA, University of Alabama, University of Montevallo, Alabama State University, Alabama A&M University, University of West Georgia, Auburn University, Jacksonville State University, Stillman College, William Carey University, UAB, UAH, which is University of Alabama in Huntsville, University of West Alabama, Troy University, University of South Alabama. Then, in addition to University of Alabama being there, the University of Alabama College of Continuing Studies will be there. Athens State, or they've been invited to be anyway. Athens State University. And in addition to UAB being there, they've invited the UAB School of Health Professions to be there. University of North Alabama, Samford University, Alcorn State University, Kentucky State University, Tennessee State University, Faulkner University, Southeastern Bible College, Talladega College, and Georgia Southwestern State University. Wow. Now, that will be Wednesday, February 12th, Birmingham West Campus, the B building. The next day, Thursday the 13th, the same schools have been invited to come here to this campus. And again, that'll be 9:30 to 11:30 in the morning. And this will be, I kind of doubt it's going to be the Vassar campus cafeteria in Building A, because that's the end of the breakfast crowd and at the beginning of the lunch crowd. I doubt if they're going to be in the cafeteria. My guess is what they mean, they're going to be in the faculty staff dining room, which is just adjacent to the cafeteria. I don't know that for sure, but that's my guess. All right. So that's that. Now, this next one, there's not much you can do to prepare too much for that, maybe a few things, getting your resume together, that kind of stuff. But applications, that kind of stuff. This one, there is plenty you can do to get started on this. Are you interested in poetry? Okay. You may be in this. This is Power Optimization of Electrothermal Systems. POETS. Okay? Not quite the same poetry you had in mind. This is a research experience for undergraduates. And the guy who sent this, Joseph Muskin, runs a summer research program for the Center for Power Optimization of Electrothermal Systems, that's POETS. We are looking to recruit minority engineering students to work at 3 of our 4 institutions for this summer. That's University of Illinois, University of Arkansas, and Howard University. It's a 10-week internship, exposes undergraduates, and blah, blah, blah. Okay. So I'm going to leave this up here. There's too much really to read, but there's plenty to look at, and see. There's also this brochure, which I kind of pieced together, and that is shown here, and there's some of the same information, a little bit more detail. So that will be up here if you are interested in pursuing it. Here it is. Okay. Now, still don't see Josh, so I guess we'll go on and get started. Any questions from anything we've done up till now? We did get started last time. We went through all the preliminary stuff and actually did get started in 1.1. All right. No questions? Okay. We're on the top of page 3 in section 1.1. Chapter 1 is Systems of Linear Equations, and 1.1 is Introduction to Systems of Linear Equations, very close to the same title. And we talked about what the solution for an equation is. We haven't quite gotten the system yet, but we've gotten the solution of an equation. And on the top of page 3, sort of like the second paragraph down, just before you get to example 2, a set of all solutions of a linear equation is called a solution set. Okay, I guess maybe I ought to write that. That's sort of an important concept. The set of all solutions, and I abbreviate like crazy, solutions of a linear equation, abbreviate like crazy, is called the solution set. Okay. When you've found this set, you've solved the equation. So if you find all those possible solutions, then we say you have solved the equation. Okay. Now, to describe the entire solution set of a linear equation, we typically use a parametric representation. That's what we're going to be doing in example 2 and 3. So let's start with example 2. I'm going to erase that definition. It says solve the linear equation x sub 1 plus 2x sub 2 is equal to 4. Okay? Now, can you give me a solution to that? Think of any solution to that equation. I'll show you a couple very easy ones. Let's just first assume x2 is 0 and what the x1 is. 4. So 4, 0 would be a solution. Okay? And mark this recalcitrant student here. No, I'm sorry, Josh here. Okay. Can you do another one? Let's assume that was 0. 0, 2. So 4, 0 would be one solution. 0, 2 would be another. You have an infinite number of those. You could do 1, 3 halves. Yeah, that would work. Or you could do, that'd be 1, it'd be 2, 1. That would work. There's an infinite number of solutions. Okay? Now, I don't want to write an infinite number of solutions down. I want to use a shorthand. Okay? So here's what we do to get the shorthand. Okay? Now, there are several ways you can approach it. I, being lazy, like to come up with the easiest way to do it. Now, some of you may be hard workers. That's fine. That's perfectly fine. You can still do this, but to me, it's so much easier to find the easiest way to do it. Okay? So here's what I'm going to do. What's the easiest thing to solve for in that equation? x sub 1. So let's do it. X sub 1 is equal to, tell me. Okay. I'm a little lazier than you, obviously, because I would like to say it as 4 minus 2x sub 2. It doesn't matter. It's just that you had to write two symbols, a minus and a plus. I only had to write minus. I was just being lazy, okay? Now, either way you do it, it's fine. Now, at this point, the one you know the most about is this one, because it's equal to that. The one you know the least about is your x2, right? It can be just about anything. So let's just pick in anything to call it. And we call that the parameter. Okay? So you happen to know what the favorite name for a parameter is? There's several, but you can use just about anything. I would not use x. Pick another parameter. Because x is in the problem. P would be fine. Believe it or not, the most common is T. Okay? P would be perfectly fine. That makes more sense than T to me, but they almost always use T. So what they say in that form, x sub 2 is called the free variable. In other words, the independent variable. X sub 1 is the dependent variable, because the value for x sub 1 depends on the value for x sub 2. So, since that is the free variable, then name it as a parameter, and the book uses T. So let T equal x sub 2. Let that be your free variable. If so, T is equal to x sub 2, what would x sub 1 be? 4 minus 2t. So now we can set our ordered pairs, because every solution we had was an ordered pair, x1, x2, right? So let's do it. The set of ordered pairs, 4, I can't write, 4 minus 2t, comma t. There's your ordered pair. And remember when we said t equals 0, that would be 4, 0. That's one that we had, remember? And when t was equal to 2, this would be 4 minus 4 would be 0, 2. That was one we had. And then we could have done that. Remember we said t equal, I think it was 1/2, wasn't it? Yeah, 3, 1/2. Okay? It has them all. Pick a t, any t, you can get an ordered pair. Okay? That is what we mean by parametric form. Okay? Solve for one of the variables, and the one that's you know the least about will be your free variable or your independent variable. Let your parameter be that, and then go from there. Okay. Now, if you had, for some reason, obviously not being lazy enough, chosen to solve for x2 rather than x1, what would that be?
4 minus x sub 1
Would equal to 2 x sub 2, right? And then divide both sides by 2. So that gives you x sub 2 is equal to 2 minus 1/2 x sub 1. In that case, what's your free variable? X sub 1. So now they don't want to use the same parameter, so their next favorite is S. So you could say, I'm sorry? No one came at all. Was that one student paid or not paid? Do you remember?
It's registered. We're probably paid.
Huh?
It's registered. We're probably paid. I don't know.
Okay. On your attendance, when you do it, if there's an asterisk by the name, they haven't paid. If there's no asterisk, they have paid. So when you go to the, okay. Sorry, I forgot to. Well, y'all are both here, so you know what's going on. Okay. All right. So there's another way to express it. The same solution set could be expressed as S, comma, 2 minus S over 2. Okay. That gives you the same thing. Let's just see if it does. When S was equal to 4, that would be 2 minus 4 over 2 is 2 minus 2 is 0. Sure enough, same thing we got there. When S was equal to 2, I believe it was. No, we didn't do that. X equals 0, 0, 2. So every ordered pair we got here, we got it there too. Okay? So there's not a unique parametric expression, but sometimes these are easy. To me, this is the easier. It doesn't have a fraction. That one's just a little more complicated, a couple does. Okay? But both of those are perfectly legitimate parametric expressions for that solution set. Okay? All right. Let's do example 3. Any questions on example 2? Example 3. Let's solve this linear equation. 3x plus 2y minus z is equal to 3. It says solve it. That means we come up with all the solutions. Okay? How would you proceed? Say again? You may have said it right. I just don't hear well.
No, I'll do.
Second?
Z.
Say that again.
Z.
Yes, I like to solve for z because that's the simplest to solve for. So what would your z be?
3x plus 2y minus 3.
Perfect. Okay. Now, what is your independent and your dependent variable here?
That would be 3x plus 2y.
Okay. Okay. Your x and your y are both independent variables. Because you see, z depends on those two. But they don't depend on each other. So they're both independent. Okay? They're both free variables. So in this case, we will say let 3x equal, well, actually, I wouldn't say 3x. Wait, let me get. Let's just pick a variable. Let x equal what? T, and let y equal s. That sounds as good as any. I think probably in the book they'll reverse order, but it doesn't really matter. Then z is going to be 3t plus 2s minus 3. So now your ordered triplet, which will be your solution for any of these, would be t, that's your x, y is s, and z is 3t plus 2s minus 3. Okay, that's sort of ugly, so let me see if I can clean it up just a little bit. Okay, there is your parametric form. You have two parameters now, s and t, because you had two free variables. Okay, so that's a two-parameter system. One equation, but it's in 3 dimensions. So you can have one dimension fixed and the other two depending on it. Okay. Let's see how the book did. They chose X and Z to be the free variables. Dumb choice. I mean, it's okay, but okay. Solve for X, and then you get fractional forms, and then they get those that representation. I like ours better. Okay. All right. Now, so far we've only dealt with equations. Okay? We've only dealt with equations and come up with solutions for an equation. Now we're going to deal with systems of linear equations. Finally, we get to what the chapter is about and what the introduction is about in 1.1 is a system of linear equations. Now, what is it that makes a linear equation linear? Exponent of every variable can only be the number 1. Okay? So, here is an example of a system of m linear equations in n variables. Okay? So you got to have m equations and n variables. So how we usually express it, the coefficients are given the letter A, and they're given a double subscript. The first subscript represents which equation you're talking about, and the second subscript talks about which variable it's a coefficient for. So that would be a sub 1, 1, x sub 1, plus a sub, still the same equation, 1, 2, but it's a different variable, x sub 2, plus a sub 1, 3, x sub 3, plus dot, 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 plus, remember we said n variables, so that would be a sub 1, still first equation, n, x sub n, is equal to, I think they just call this b1. Okay, whatever that constant is, that's the constant for the first equation. There is an equation in n variables, but we want a system of these, m of them in fact, so the second would be a sub, you tell me what the subscripts will be. Two, 1, what variable? X, which way? X. X sub 1 plus 2, 2, x sub 2 plus a 2, 3, x sub 3 plus dot, 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 all the way up to and including a sub 2n, x sub n, and that would be equal to b2. Okay. We'll do the third one. What would that be? 3, 1, x sub 1 plus 3, 2, x sub 2 plus a 3, 3, x sub 3 plus dot, 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 plus 3n x sub n is equal to b3. And we'll continue down, dot, 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 everywhere a dot, dot, okay. Even there, dot, 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 okay. And what would be the last equation? Remember we said m equations, so that would be a sub m1 x sub 1 plus m2 x sub 2 plus a sub m3 x sub 3 plus dot, 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 plus a sub m n x sub n is equal to, okay, the nurse would call that bowel movement. No, we won't say that. Okay, now, there is our system of equations. You have m equations and n variables, okay? And the m's and n's can be whatever, okay, whatever number. Those are all integers, okay? Now, what is the solution of such a system of linear equations? These are always linear equations. Why? Because every variable in every equation, the maximum, the only exponent it has is 1. Only possibility. Okay. So the solution of that is a sequence of numbers, s sub 1, s sub 2, s sub 3, ... up to and including s sub what? N, okay, because you have n variables. You have to have some solution for each one of those. Now, remember, they could be individual numbers, or they could be parametric expressions, whatever. But that's going to be your solution set. The set of all s's, and you're going to have n of them because you had n variables, such that you have that. Now, let's actually do one. All right, to erase? You got it, or are you still writing?
Still right.
Okay. All right? Okay. Here's a pretty simple one. 3 x sub 1 plus 2 x sub 2 is equal to 3 minus x sub 1 plus x sub 2 is equal to 4. Okay. Now, I don't know if you remember doing this in your past life sometime. Do you? What's one way to solve that system of equations? There's actually a couple of different approaches you can make. Pick one of them, either one, let me know how you choose it. Second? Okay, you're just going to guess a few? That's certainly one way to do, but it's going to be long and tedious, unfortunately. There are at least 2 techniques for solving this. Well, 3. I can think of 3 techniques. One, you could do a graph of first the first equation, then the second equation, and see if they ever cross. If they cross, that's going to be a solution. That's a little tedious. Not bad, but a little tedious. Okay? Especially if it was 3 dimensions, that would really be tedious. Okay? This is just 2, so that wouldn't be too bad. There's another called the substitution method. And that way, I would take the simplest of those 2 equations, the bottom one, in fact, and say x2 is equal to 4 plus x1, right? And then, in the top equation, instead of x2, put 4 plus x1, and then you have an equation in terms of x1, solve that for x1, then go back and plug in for x2. That's called substitution. Generally, the easier of those 3 methods will be this one. It's called substitution by elimination by addition. Okay? And here's what I would do for it. And you have 2 choices here. Okay? And me being lazy, I won't pick the easiest one, but one of them's a little easier in one sense, the other's a little easier in the other sense. In one sense, since you have opposite signs here, just multiply this equation by 3, everything in this equation by 3, and when you add them together, you eliminate the x1. On the other hand, this is a simpler number, so multiply this equation by -2, but you have to multiply all those by -2. So it's whether I make more mistakes doing minus signs or using bigger numbers. It just depends on which is easier for you. And then you add them together, then you eliminate this one, and you get the other. And then once you get the first, you can substitute and get the second. Which you want to do? Multiply this by 3 or that by -2? You want to do that, okay? All right, so let's multiply the second equation by -2. So I'm going to write the first equation again. 3x1, I thought I was going to write it.
I got a question.
Sure.
Why are you multiplying it by -2 if it's positive?
Okay, let me, number one, you told me to, but number two, let me show you, okay? So I'm going to write down the first equation, 3x1 plus 2x2 is equal to 3. Okay, that one I'm leaving alone. In the second equation, I'm writing multiply -2 times -x1, you get 2x1. Multiply -2 by x2, you get -2x2 is equal to, multiply -2 by 4, you get a -8. Okay? Now here's why I multiply by minus rather than plus. When I add those two together, you eliminate the x2. That's why I do it, to eliminate by addition. Okay. Now, don't get too wrapped up in this. We're not going to do that many of them. We're going to do a different technique later. But you see, this eliminates that, and now we get 5x1, when we add those two equations together, right? Plus 0 is equal to what? -5, and that's pretty easy to solve. x1 is equal to -1. Now plug back in either one of the equations. I like the second one better. -x1 plus x2 is equal to 4. Okay? Now, plugging in a -1 there for x1, you get 1 plus x2 is equal to 4. And that's pretty easy to solve for x2. What would that be? 3. Okay. So here's your solution set. -1, 3. x1, x2. One and only one solution. Okay? Those others we had parametric equations which you have infinite number of solutions. This one you only have one solution. Okay? And here's why you only have one solution. Those are two different lines. And what's more, they have different slopes. So if you have one line like this and another line with a different slope like this, there's only going to be one point of intersection. Now, if those were the same lines, in other words, one was just a multiple of the other, you'd have an infinite number of solutions. There you would need your parametric equations. Or you could have had two different lines, but with the same slope, they're never going to cross. That would have no solutions. Now, I'm jumping a little bit ahead, but that's your condition in every set of linear equations. System of linear equations. You're either going to have one unique solution, no solutions, or an infinite number of solutions. Every set, no matter if we had n by m, they're always going to wind up one of those three. Okay. And that is the only solution. -1, 3. Okay? If you had chosen any other x of 1, other than -1, you'll never get another solution for x of 2. It just won't work. All right. Now, this is a big boo hiss, but what I'm going to do is do what they say. This is a discovery in the middle of page 4. Okay, it says graph the two lines. And here's the first line. 3x minus y is equal to 1. And the next line is 2x minus y is equal to 0. Okay? Now, how would you go about graphing that first equation? I want to see how lazy you are. You- Y is equal to what? 3x plus 1, is that what you said? Or is it minus 1? Second? You sure? Okay. Okay. Yeah. Yeah. What I did, I moved the y to that side, meaning I had to move the 1 to this side. Now, here's my dumb little way of thinking about it. You see, here the x's and the constants are on opposite sides, and they have the same sign. And they wind up on the... Did I do that right? No, that's not a minus there, that's a plus. Was I listening to you? What was I thinking? Okay. Because you moved the y and you kept the x where it was. Okay. Now, I'll show you my little rule. Since these have the same side when they're on the opposite sides of the equation, when you put on the same sign, they better have opposite sign. Okay? So, that gives us that. Now, why did you do that? What does that tell you? Does that help you graph this?
Yeah.
How? Okay, you could, even easier than that. Okay, this is in slope-intercept form. So your intercept is minus 1. The y-intercept is minus 1. It's right down there. And what is the 3?
That's the slope.
The slope. So you go from that point that you know is on there, up 3, right 1. Up 3, right 1. Okay? Or, to get a slope of 3, you could go down 3, left 1. Down 3, left 1. Okay? So there is, if I could draw straight lines, there would be your graph of that linear equation. Every point on that line is a solution. Every one of them. Okay? What do you do with the second equation? Y is equal to 2x. Is that what you said? Yeah. Okay, where would you start there? Okay, at the origin, 0, 0 is obviously on that. That's your y-intercept. And then what do you have then? Slope of 2. Up 2, right 1. I know my point of intersection right there. Up 2, right 1, up 2, right 1. Or down 2, left 1, down 2, left 1, down 2, left 1. There would be that equation. One and only one point of intersection. Now, if I were doing this freehand, I did, but and was not very careful here, it looks like my point of intersection is down here. But I knew that was the point of intersection because it came out the same in both cases. But, you know, it can be a pain in the neck to graph, okay? But we do get a solution, okay? Now, where do they intersect? The point, say again? 1, 2. Okay. How many solutions does that system of linear equations have? One solution. Okay. Now let's do number 2. Let's do number 2 in a different color. Give me a color. Say again? Blue. Carolina blue or dark blue? Carolina blue. Okay. Well chosen. Okay. Repeat this analysis for the 3x minus 1 equal 3x minus y equal 1 is exactly the same first equation. So we're going to leave that alone. The second equation then is 3x minus y is equal to 0. So what would you do with that second equation? Y is equal to 3x. Can you give me some points on that one? Okay, 0, 0 for sure. Up 3, right 1. Up 3, right 1. Or down 3, left 1. Down 3, left 1. So here would be my really ugly, somewhat straight line. What do you notice about it in the first equation, which is this one here? This one and that. They're parallel, okay? How many solutions do you have? Oh, wait, where do they intersect? No. Okay, no, okay. It's not these two. It's this one and that. The first one is that. I probably should have done 3 different colors. This is my first equation. That was my second equation. This is my second equation. And those two do not intersect anywhere. Not here, not anywhere. Because they are same slope. The slope is 3 in both of them, but different y-intercepts. So they will never cross. So where do they intersect? They do not. How many solutions does that system of linear equations have? Say again? Yeah, no solutions at all, period, ever. All right. Now, here's another set of equations. What color you want these? Red. Okay. Dark red or bright red? Bright red. Okay. Here's the third set. The first equation identical with the first equation of the other two. The only difference here is the second equation is 6x minus 2y is equal to 2. Okay? What would you do to deal with that one? Divide everything by negative 2? Or maybe just 2? Let's just do 2. So divide everything by 2 and what do you get? 6 divided by 2 is? 3x. It's not plus, you divide it by, okay, minus y, not 1, but okay, minus 1y would be okay, is equal to 1. And guess what that is? That's that first equation all over again. And if you were to plot those points, here is what you would get. You would get this line right here. Okay. That's your first equation. That's also the second equation. How many points of intersection do you have? Say again? Really? Here's your first equation, and there's the second equation.
You have all of them.
Everything, an infinite number of solutions. Every point on this line is also a point on this line, because they're the same line. Okay? So you have an infinite number of solutions. Okay? Or where do they intersect? Everywhere. Okay? How many solutions? An infinite number of solutions. Okay. Now, before I move on to the top of page 5, let's just do the bottom of page 4. Linear algebra applied, here is, and let's see, I'm trying to remember, didn't you take Chem 111? Okay, you're used to seeing these, aren't you? Equations with, this is methane plus oxygen. You're oxidizing methane, in other words, you're burning it. You get carbon dioxide and water as a byproduct, right? And they just put down your coefficients, x of 1, x of 2, x of 3, and x of 4. That's how many molecules you have of those when you do it. Then you're trying to balance that chemical equation. Now, I know how I would do it, and it's probably different from how they would do it, but I would just immediately say, let's let x1 and x1 and x3 be 1, because the number of carbons have to be the same, okay? Then that would mean you have 4 hydrogens on the left-hand side of the equation, and to get 4 hydrogens on the right-hand side, x of 4 has to be 2, right? And then you have 2 oxygens with the 1 carbon dioxide, and you have 2 oxygens with the 2 waters, so that's 4, so x of 2 has to be 2 as well. Now, that's how I do it chemically, but you could do it using linear algebra as well. I just don't really see how that's any easier, but we'll leave it like that. Now, before we move on, let's get a little bit of terminology here, okay? The first bit of terminology is the concept of consistent and inconsistent equations. This was a consistent set of equations because it had a solution. Only one, but it had a solution. This one was an inconsistent set. No, I'm sorry. This was the first. These two were consistent because it had a solution. This one and this one were inconsistent because they never intersected. That's inconsistent. This one and this one were consistent because they have an infinite number of solutions. So anytime you get a solution, whether it's one or an infinite number, they're consistent. It's only when you have no solution, like this one and that one, no solutions because they never intersect, that's called inconsistent. Now, they're not doing it in the book now, but because I always think of them together, there is another concept here, and that's independent and dependent. Okay? These two equations, this one and this one, are independent of each other because they do 2 different lines. Okay? This one and this one are independent of each other because it's 2 different lines. But this one and this one are the same line. So therefore, that's a dependent system. Okay? So this system would be a consistent, independent equation. Consistent system, independent equations. These two would be an inconsistent system. Now, inconsistent system, we usually don't talk about dependence or independence. So I sort of said that wrong. We just say it's inconsistent. But these two would be consistent because they have solutions, in fact, an infinite number, but they would be dependent because this equation is exactly twice that. So they're dependent on each other. These two are not dependent. They're completely separate. Okay. So the book that uses dependence, independence, later we will talk about that. But I thought let's go on and throw it out there now. Okay. So let's do example 4. Yuck. They say grapheme. I hate graph. I mean, well, it actually says solve and graph. Okay? And I think I'll do that. Okay? Here's the system of equations. Let me go back to my basic black here. Now, by the way, I don't have my watch. My battery died, so y'all are going to have to let me know when it's time, okay?
15 minutes.
Huh?
15 minutes.
15 minutes, okay. Somehow knew y'all would somehow tell me that. Okay, x plus y is equal to 3, and x minus y is equal to minus 1. Okay. Now, can you look at those two equations and tell me whether they're independent or dependent? I'm sorry, whether they're consistent or inconsistent?
They're consistent.
They are consistent. Why? What gave it away?
They have the same slopes as an opposite.
No, they don't have the same slope. They have different slopes. Oh, wait, same slope, opposite signs? Oh, yeah, that's different slopes. Okay. Anytime you have two different slopes, that's going to be a consistent system. You could also have a consistent system with the same slope, but they would have this. They would be just multiples of each other. Okay. But these have different slopes, one positive, one negative. So they've got to be consistent. Okay. Can you give me the solution easily, or you want to graph it? Notice how I phrase that. But something be easier than graphing. Second? Not quite, but add them together. Elimination by addition. Notice you have same coefficient, opposite signs. So just add them together. What do you get? 2x plus 0 is equal to 2. Guess what? X equal 1. Now pick either one of them. I really don't care which. I want the top one, I think, so I do care. That'd be 1 plus y equal 3. Guess what y is? Y is equal to 2. Consistent system, it has a solution. Independent equations because it's one and only one solution. Okay? So we found our solution, 1, 2. Okay? I could go back and plug that in. Seems like we had that before, didn't we? Okay? But this is a different equation. Now, I wanted to say this before, but y'all were doing so well with what you had before. There is sort of an easier way to graph this one especially. The others, it could have done too, but it sort of goes back to something I did before. We know this point is going to be common to both of them. But here's another thing we can do. Let's set this equals 0, and what do we get? X equals 3. So 3, 0 is also a point. 3, 0, there's a point. Oh, we ought to do different colors. What color you want the second equation to be? Red, bright red again. So this one is going to be bright red. The other is going to be black. Okay? Now let's do almost the same thing we did there, except this time we'll let this be 0. And what do you get? Second? Y equals 3. So 0, 3 would be your ordered pair. So 0, what happened to my 2, 1? 0, 3 would be my ordered pair. I think I know what that first line looks like. Isn't it like, I can't draw straight lines, obviously. Okay. Actually, the way I do it best is go on and plug them all in. Okay. Okay. That's going to be my best interpretation of the straight line. Okay. The red one then, going to do something fairly similar. Okay. We know that 1.12 is going to be on it. So I could go on and make that red. Or at least we think it is. Now let's just do the same thing we did before. Which one are you going to cover first?
Cover the y.
Y, okay. So let that be 0. What do you have? X equals -1, 0. -1, 0. That would be right there. And then let's do the other one. Let X be 0, and you have Y is equal to 1. And there we have that one. And sure enough, again, I have trouble drawing straight lines. Actually, that's a redundancy, isn't it? Can you draw a line that's not straight? No, it's not a line. Okay, so okay. Now, this has nothing to do with the exercise, but I just want to ask you a question. Anything special about those two intersecting lines? Anything special about those two intersecting lines? They are perpendicular. How can you tell that without looking at that? Because I can't tell for certain they're perpendicular. How does this tell you?
They have opposite slopes.
Exactly. Same number of, wait, not quite.
I mean, one's positive,
opposite, opposite reciprocals. Okay, opposite, positive, negative, but also reciprocals. The slope of the top one is -1, and the slope of the bottom one is +1. Those are negative reciprocals of each other. This isn't that they're opposite signs. -1/2 and +1/2 are not perpendicular. But -1/2 and +2 are. Okay, they have to be negative reciprocals, and that is a negative reciprocal. Okay, that was beside the point. Okay, so we solved and graphed the first one. That's the A. Let's do B then. And B, our first equation is still going to be black, but the second equation will be what color? Not black or red. Blue. Carolina again? Okay. So the B, the second equation will be 2x plus 2y is equal to 6. Okay? Now, I would say do it the same way we did before, but this is an easier first step. What do you reckon that's going to be? But a little louder, I don't hear well.
So there's going to be an infinite amount of solutions.
Why?
It's just the different. It's divisible by 2.
Yes, when you divide this one by 2, you get x plus y equals 3, which is exactly the first equation. So that would be this one here. An infinite number of solutions. It is a consistent system. Now the red's not even part of this one. The black and the blue are. They are consistent because you have a solution. You in fact have an infinite number of solutions, but these are dependent equations. The second one is twice the first one. Okay? So let's do the C. What color you want the second equation to be here? Green? Light green or dark green? Light green. Okay. Pale green. Okay. And the first equation is the same, so the black one's still good, but the second one is x plus y equal 1. Okay? What can you tell me about that? The slope is -1, which is exactly what the slope of the black equation is. But what's different about it? The y-intercepts are different. So, and what's the y-intercept of the second one? Yes, +1. Okay? You mean physical science? Yeah, but it starts at 115. Okay. Yeah. So it has a -1 slope. So it's the same slope as the last one, but different y-intercept, which means what? Inconsistent system, there are no solutions. The two lines are parallel to each other. Very good. Okay? Now, the first one we had a solution. I'll put it in red. Oh, I didn't put it in red, did I? Okay, that was your solution. In the second one, we had an infinite number of solutions. What if I say I want an ordered pair to represent that infinite number of solutions? What could you say then?
Just pick an ordered pair.
Say again?
You just pick an ordered pair from the graph.
Yeah, but not just an ordered pair. I want all the ordered pairs.
Negative infinity, positive
Okay, certainly your x's and y's go there, but here's what I'm getting at. I want an ordered pair. Now this is the blue one, okay? Carolina blue. Okay. Remember, these two equations are exactly the same equations, right? So I'm going to use a simpler one. X plus y equal 3 when I divided both sides of that, everything on both sides by 2. Then I would get, and this is what you did too, I think, y is equal to minus x plus 3, right? Now remember what we did before? Which was your free variable or your independent variable, and which was your dependent? Okay, and what you let that be? Let x equal t. Then y is equal to? Or 3 minus t. I just don't like writing any more signs than I have to. I'm lazy. So your ordered pair here is t 3 minus t. And sure enough, that gives you every solution. Yo! I almost destroyed my computer. I don't know why it does weird things like that. Okay. All right. Let's let t equals 0, that be 0, 3. And sure enough, 0, 3 is on there. Let's let t equal 3, and you get 3, 0. 3 zeros on there. Every point will be on there. T equal 2, that be 2, 1. 2, 1. Yeah, that's one. Remember, we already had that, okay? This is your ordered pair. It gives every solution. This is the only ordered pair here, and this last one had no ordered pairs because there's no point of intersections. Okay. And you see graphs very similar to what we did. Now, how are we doing on time? 5 minutes. Okay. In example 4, and also in that discovery we did earlier, for a system of linear equations, precisely one of the following is true. Number 1, let's go back to black. Easier to read. Number 1, the system has exactly one solution. Okay? What kind of system is that? Consistent. Okay? It's a consistent system. Now, it doesn't matter which order, but the system has infinitely many solutions. What kind of system is that? It's also consistent, but the two equations are dependent. Okay? So we don't call the system dependent, but the equations are dependent. One depends on the other. And then the third possibility is the system has no solutions. You're absolutely right. S-O-L-N-S. And what do you say about that one? Inconsistent. And this one up here, since there is only one solution, these two equations would be independent. Okay. The book isn't talking about those yet. We'll do it later. So that's the key block at the bottom of page 5. Okay. Now, how are we doing on time?
2 minutes.
2 minutes. All right, I think we can answer the first question here. It's just going to take me almost 2 minutes to write it, but I think you'll find the answer to it pretty easy to do. Here we have an equation, x minus 2y plus 3z is equal to 9, minus x plus 3y is equal to minus 4, and 2x minus 5y plus 5z is equal to 17. There's one system of equations. 3 equations, 3 unknowns. Here's another one. X minus 2y plus 3z is equal to 9. Okay? Happens to be the same first equation. The second equation here, though, is y plus 3z is equal to 5. And the third one is just simply z is equal to 2. Which of those two systems do you think is easier to solve? Well, the second system, okay? And the reason is exactly what you gave. Because you already know one of the 3 values, z is equal to 2. But since you know that one, you can plug z equal 2 here, and you get y plus 6 is equal to 5, so now I know what y is. Negative 1, right? And since I know that y is negative 1 and z is equal to 2, then this would be x plus 2 plus 6 is equal to 9. Well, 2 plus 6 is 8, so x has to be equal 1. Ha, that one's pretty easy to solve. This one going to take a lot more work. Okay. Now, what is not obvious, and it's not at all intuitively obvious, so don't expect it to be, these are what we call equivalent systems. They have the same solutions. Now, what did we say it was? This one was negative 1, was it? Or 1? 1, I think. 1, negative 1, 2. What was that? Let's see if that works here. 1 minus 2, no, minus, that would be plus 2. That would be 3, no, yep. Plus 6 is 9. Yep, that one works. We knew it did. Okay? This would be minus 1. Minus 3 would be minus 4, and this was 2 plus 5, that would be 7, plus 10 would be 17. Yeah. They have the same solution, so therefore they're equivalent solutions, equivalent systems, and this one's so much easier to solve. So what we're going to do next is see if we can manage some way to figure out how to make this system become that system. Then it's easier to solve. Elimination by addition works okay for 2 by 2. Substitution sort of works, graphing sort of works. Don't try any of those with this one, okay? There is a technique though, and that's what we're getting at. I think I just did example 5, okay? Didn't realize that what we were doing, but it is. And I think we just did example, you can come on in, example 6. And I think I just did the definition at the bottom of the page. They are equivalent systems. Okay, so we'll be starting next time with page 7. Top of the page, including the picture of this handsome, handsome character here, called Friedrich Gauss. Okay. So we'll begin at the top of page 7. Now let me give you your homework exercises here.
Are you the only one?
No, one person left already. We have 2 in this class. Okay. You can do any of the odds 1 through 5, any of the odds 7 or 9, either 7 or 9, any of the odds 11 through 23, and some of those are real pains in the neck. And you can start doing any of the odds 27 through 29. and we will pick up the rest of those next time. And by the way, all these exercises, the odds are in the back of the book, but also calchat.com. So, all right, good deal. We'll see you next time. Yeah. That's a linear algebra class. Both of them need it to graduate, so I'm teaching 2 people. All right. Let me end this.